Welcome, everyone. So, I heard a rumor last month that BayPiggies was dead. I heard that we couldn't get attendance. But as I look around the room, I know that's not true. I heard that we couldn't get organizers, and I think we'll show that that's not true soon. And I heard that we couldn't get speakers, and I think we'll show that that's not true. But more importantly, instead of that, let's talk about what I want to just tell you what I personally believe. I believe in an open source community. I believe in the transparency that it would give. I believe in the community that forms around it, just like you and all of us. Okay? So we're one of the oldest open source communities that have been around. We were around long before other websites were around. We were actually an old email list. We've been around for a very long time. In fact, it's on that list that I still today see new people asking questions, and Guido himself, the person who wrote the Python and programming language, is actually answering those questions himself. When it's just a really nice to see the expert level, the other level, and everyone as a community helping each other. Where do we live? I think there's a little bit of confusion in the past of what BayPiggies is. BayPiggies has been a list. It's actually BayPiggies at python.org. It's been around, I think, since 2001 at least. I think longer than that. The main webpage is actually baypiggies.net. That's where actually people are going to. And BayPiggies, by the way, is the Bay Area Python Interest Group. If you go to the lower left-hand corner, you will actually see how to sign up for that list. And that's actually where most of the communication is happening, where the core group has been around for a very long time. But we also use Meetup for an outreach. And Meetup meets a lot of people. We get a lot of new faces to bring into the community, and Meetup is awesome for that. I'm just curious, how many people knew about the list before tonight? Raise your hand. Okay, I'm seeing about eighth of the room. How many people heard from Meetup? Okay, so I still don't know where half the room met from, okay. How many heard, we have lots of people who volunteered. How many heard from the Pi for Science at Berkeley? Okay, well, welcome however you found your way here. This is really, really good. So we have, do you have to be a famous programmer to participate? Do you have to be like this world famous great programmer to lead people to this room? Or stand by the door and let us in when you're late, who, by the way, thank you, Bo, for doing it right now. To introduce speakers, like myself, for introducing speakers, do you have to be this great programmer, or do you even have to be a programmer at all? Do you have to be a programmer to solicit speakers, to moderate the email list, be a co-organizer, and stand in front? And the answer is no. This is a community where we like helping each other, and if you want to become involved in the community, you can just become involved in the community. You don't have to pass a test. No one's going to pair program with you and say, I'm not sure if you can let people in until let me see if you can red, green, black refactor, maybe. No, we'll help, if you want to help, we'll help out. We're not going to make you do a whiteboard test before we say, hey, by the way, can you show people where the bathrooms are? So if you would like to help out, please email me. My name is, I didn't put my name and email address on this slide. My name is Glenn Jarvis. My email address is hopefully pretty easy to remember. It's Glenn with one N. So glenn@glennjarvis.com. And I'll make sure to blast it out so that people have a way of seeing it soon. But before we talk about me, I want to talk about our other volunteers. I put a word out saying I need a little help this time, where we kind of need some help to volunteer. So thank you, Jeff, by the way, for taking care of all of February. Grant, for counting all the people in this room and taking care of the stuff to make sure we have enough room. And I couldn't even tell you there's just so much help that we're getting already. Blythe, Tom, Mo, Paula, James, Brian, Ralph, Vicky. Thank you again. Without you, we wouldn't be able to have this, so we are a community. So, yeah, give yourselves a hand. Also, we have some pretty good speakers. David, I'm going to introduce in a few moments. Awesome. I'm very excited about his talk, actually. So I'm very excited to see what this is, to hear David's talk. And in February, we're going to have Dan, who, by the way, is right here as well. Dan's shy in the corner. Matt is going to be here for March. And then right before PyCon, everyone likes to practice. Smaller audience. You did a better job before PyCon starts. So Daniel's already stepped up to say we're going to practice for PyCon in April. If you want to practice too, please come see me. Again, it's glenn@glennjarvis.com, that bottom name there. May, Suman's going to talk to us, and then I'm going to do something in June about how to use get and use Python to actually manipulate get. So don't believe every rumor that you hear. We have an audience, as you can see looking around the room. We have organizers, as you see a list of over 10, 11 people already. And I think there's more. Did I forget someone on the list? If so, could you stand up now? Oh, Sarah, please stand up. I'm sorry. Sarah, thank you. Would any of the other volunteers would like to just step up for a second? Grant, would you mind? I don't want to put everyone on the spot, but now you're on the spot. Grant, thank you. Everyone else who's on the list, you want to just stand up for a second? Vicky, stand up for a second. Thank you. Jeff, Tom. These people actually made it happen. It wouldn't happen without us. So please volunteer and join this great crowd. All right, don't believe everything you see. Attendance, organizers, and speakers for just half the year already. We're doing good. Let's keep it going. So in that, I'd like to start with announcements, what we typically do. Yeah, Stephen. PyCon video. We've done it before. We watch the videos from PyCon for those who can't go to PyCon. So, where's the video viewing going to be? And join the list. All right, PyCon viewing. It's awesome. Thank you, Stephen. Cool. We will definitely email on that one. So Saturday, June 10th or 17th, Stephen said. He wants to do a PyCon viewing. So announcements are a place where you can say, hey, this is what I just learned in PyCon. Oh, can you help me with this? I don't understand how twisted work. Oh, I don't understand tornado. Or can you tell me what a list comprehension is? Or I'm looking for a job. You know, lots of things. Here's a place to stand up. And in fact, jobs get such a special rating. Who's looking for a job? Do you mind standing up and giving her just a couple of minutes of what you're looking for? Somebody here might be hiring. Or not, if you don't want to. I can't use the microphone because I didn't bring my guitar. You sure? No? Okay. One mic? Okay. So don't put you on the spot if you don't want to stand up, but if you are looking for the job, just tell me what your skills are, what you're looking for, and we'll actually say, people who are looking for work, at the very end of the talk, we're going to come over here. The people who are hiring are going to come right over there, and we'll try to introduce you. All right, anyone else looking for work? You know, this is a different market than it was in 2007. Yeah. Do you want to stand up and say quickly your name and what you're looking for? Okay, it's an open developer position in Python. Awesome. All right, great. So Python developer position, and anyone else looking for work? And maybe I'll tell you what, I think a lot of people are feeling nervous tonight. We don't normally, everyone's usually standing up. I'm not going to put anyone else on the spot. We'll come over here afterwards. Who's hiring? Please, tell us about your company, what you're looking for. LinkedIn. Oh, awesome company, by the way. By the way, thank you, LinkedIn, for everything you've done. Food from LinkedIn. Location from LinkedIn. Great. And tools and Python Foundation? Anyone? Yeah, LinkedIn right in the corner if you want to talk to them as well. There are, by the way, volunteers for our space. They're the ones who are staying late just so we can have this meeting tonight. So thank you, Josh, and thank you. Thank you. Who else is hiring? No? Going once? Going twice? Okay, so I would like to, tonight, talk about David. David has been using Python extensively as his career as an astronomer. He's actually moving from astronomy to data science, and he's going to show us what he has. He got his BA in physics from Colby College in 2001, and his doctorate in astronomy at the University of Florida in 2007. And his PhD thesis is very interesting. He's going to tell you about that, I'm sure. And his work he did at the Institute of Astronomy in Mexico, I think would be awesome too. Come on up.
Okay, thank you.
You're done.
I'll make sure it shows first. Let's see. Here. Okay, so I'm going to talk to you tonight about using Python to analyze data cubes in astronomy. And the way I'm going to structure this talk is I'm going to talk some about astronomy, and then I'm going to go into the code I used in order to analyze the data. Because I feel it's important to understand a little bit about the background. It's important to understand where the data came from, what the objects were that I studied. And then from there, I can explain how the data was analyzed. I'm discussing work that I did when I was working as an investigator in Ensenada, Mexico. And there I studied planetary nebulae, working with the Planetary Nebula group in Ensenada for the National University of Mexico. So I'm going to talk about what is a planetary nebula, how the observations were acquired in the instrument that was used, and then how Python was used to study this data, and then end with some conclusions. So what is a planetary nebula? To understand this, it's important to understand a little bit about stellar evolution for a star like the Sun or a little bit bigger. So this is a small to medium-sized star. During its lifetime, it's forming hydrogen into helium in the center, in the nucleus of the star. But in time, it exhausts the hydrogen in the center, and at that point the star puffs up into what's called a red giant. Inside the star, in the interior, there's radiation pressure that's pushing outwards on the atmosphere, and that radiation pressure pushes the atmosphere out into space. That atmosphere, that gas, forms a planetary nebula. And it leaves in the center, a very hot core called a white dwarf. It's very small and it's very hot. Stars that are much more massive than the Sun explode in a supernova. So planetary nebulae, when they form, it's not an explosion, it's just puffed off of their atmosphere. The specific planetary nebulae I studied was called HB12. HB stands for Hubble. It's a Hubble catalog of planetary nebula, and this is the 12th object in this catalog. It's a young planetary nebula. It's hourglass shaped with a very tight waist. You can see in this image here taken from the Hubble Legacy Archive. And there's prominent lobes there, the beautiful hourglass shape. It has a position angle of 10 degrees, and it's tilted with respect to the plane of the sky by 38 degrees. It also has high velocity outflows as well. They're not shown in this image here, but they're outflows that are between 70 and 170 kilometers per second. That's pretty fast. And they're seen in blobs that are about 60 arc seconds from the center. Now, astronomers measure distances in the sky using degrees, minutes, and seconds. So the sky is divided into 360 degrees, each degree into 60 minutes, each minute into 60 seconds. And this image here is about 10 by 10 arc seconds. So you can kind of get an idea from that how far away, roughly, these blobs of emission are. The observations were acquired using an instrument called NIFS, which is on the telescope Gemini North. Gemini North is located in Hawaii. It has an 8.1 meter diameter mirror. That's the primary mirror. So astronomers measure, they use the size of the telescope, they define that by the size of the primary mirror. And that's in the image on the bottom here. That shows the interior of the dome. And where the primary mirror is where that large rectangle is. Above it, you can see in the slit of the dome is a round, smaller mirror called a secondary. The light is passed to the secondary, and then from there it sends it down into a hole in the primary where the instrument is. And you'll see at the bottom of the photo, there's some boxes down there, and that's the instrument. It's a twin telescope. It has another telescope called Gemini South, which is located in Chile. Since the telescopes are identical, this allows astronomers to be able to perform the same scientific project in both the northern hemisphere and the southern hemisphere. Here's an image of NIFS, which stands for Near Infrared Integral Field Spectrometer. A spectrometer is an instrument that spreads light out into a spectrum, like a rainbow. And by doing that, astronomers can study aspects about stellar objects or other objects in the sky, such as stellar temperatures, the compositions of the objects, and as well as velocities. So different chemicals emit different, when they interact with light, they emit at different wavelengths. Those are emission lines. So from that, you can identify what an object is made out of. And also, you can measure differences in velocities and use the Doppler effect to measure if the object is coming towards you, moving away from you. Oops. So the field of view for this instrument is 3 by 3 arc seconds. So it's a really small, tiny little region in the sky. Uses an image slicer, which slices the field into 29 strips. And I'll talk about this and how this works in a minute. And the spectrum that is produced from each strip of the image. Here I'm showing the regions where we acquire the observations. It has this funny diagram here because of we had a little issues in terms of what we requested for the observations on the day that we acquired. But anyway, this is the data. Field 1 is in the center. At the top is field 2, and at the bottom is field 3. So we will observe the central part of the nebula and the northern and southern part of the nebula. They were infrared spectra. So they weren't in the optical wavelengths, in the infrared. We used adaptive optics to correct for the effects of the atmosphere. So astronomers can use instruments to be able to cancel out the effects of the atmosphere, and it's as if you're looking at the object from space. So now I'm going to talk about integral field units. I'm going to give as an example a simpler instrument called Physica and talk about how that works. NIFS works in a similar way, but this gives a good idea of how these instruments work so you understand how the data was acquired. An integral field unit is a spectrograph for a field. It's ideal for extended sources like a nebula or a galaxy that you might want to observe. There are 3 types of integral field units. There's lenslets. Integral field units use lenslets, teeny tiny little lenses. There's other ones that use fibers. And the one I'm going to talk about today, and also the one that NIFS is an image slicer. This uses mirrors. So here is optical layout on the right of Physica. It consists of the red squares where the light is entering the instrument. The blue, those are reimaging optics, powered reimaging optics. The slicers, the green box on the left. There's a field mirror, a pupil mirror on the bottom right, and then fold mirrors which pass the light out to the spectrograph. So this is where all the magic happens, to take the observations you're getting from the telescope, to slice it up, rearrange it, and to output it to the spectrograph, where the light gets spread out. So let's see how that's done. So first the light passes to the reimaging mirror, and there the image is expanded twice, and now it's twice as big at the slicer. And now it gets sliced, the image gets sliced into 22 strips. So the mirrors, it consists of mirrors that are stacked together and tilted. And those strips are aligned into two lines, vertical lines like this. And that gets passed to the pupil mirror. So this is what the pupil mirrors see. Now, those lines are rearranged into one line at the field mirror. And at this point, the image plane is demagnified by 4, by 2 from the input beam. And at this point, the F15 input beam matches F8 of the spectrograph. So now the light is sent to the spectrograph. So this looks like a slit spectrograph. We'll use a slit like this in order to spread the light out. Okay, so then the light gets spread out to the spectrograph. And this is what the output data looks like. So here what you're seeing, this is in the raw image, and you're seeing each of those different strips. Those from top to bottom, those are the spectra for each of the different slices. Here the images were sliced 22 times. So you can see that all of the spectra fills the detector, and the light is, so wavelength in this case, wavelength is going left to right, and then top to bottom is, for each slice, is going north to south. You'll see this this will be a little clearer in just a minute. So I'm going to show how this gets reconstructed. So what you can do is you can squish all of the spectra into a line. So it's taking all the spectral information and squishing it back into a line. And then you can rearrange those lines back into an image. But in this case, each of the pixels in this image contains information in the third dimension. Contains information, the wavelength information, spectral information. This is what an output spectrum of NIFS looks like. So this is for the central regions in HB12. Here, NIFS use 29 different, slices image into 29 different slices. And so the spectra are going from the bottom to the top in this case. And here I point out an emission line of hydrogen called bracket gamma. So that's where you see it's a little brighter there in that spectrum. Astronomers use FITS files. This is how most of the data that's saved, the astronomers have used is in this format. It stands for Flexible Image Transport System. They contain an extensive header, and they're used to store information and images. And the extensive header contains information such as the observing conditions, the weather conditions, the location of the observatory, and also you can put in history as well, any modifications that were made to the file, storing absolutely everything, anything that happened to that file, to make it very scientifically accurate. And the header consists of keyword value pairs. Here's an example. An example of a FITS header on the left. You can see the keys, and in the middle, those are the values. On the far right, beyond the diagonal line, those are comments. So it consists of a lot of information here that you can see. The name of the object, where the object was observed, the position of the telescope, a lot of information. Okay, so I've talked a little bit about rearranging the images and creating spectra and then rearranging it to produce what you can produce what's called a Datacube. So here, this is a rearranged image where each pixel, if you remember, has spectral information. This is the central part of HB12, so it's very bright in the center. So it's in x and y dimensions, but along the z dimension, this is where the spectral information is. This is where the light gets spread out. So remember I talked about a rainbow. It's like where light's getting spread out. So you have the red part of the rainbow, you can imagine it's down to the left. The blue part of the rainbow is up to the right. But this, in this case, this is infrared. So remember, this is not optical. So what you're seeing here, that bright light line that goes along there, that's at the nucleus of Hb12. That's continuum emission. That's what astronomers call it, because that's emission from the central star. Stars emit light across in a wide wavelength range. But planetary nebula doesn't. Planetary nebula consists of specific elements, like hydrogen and helium and neon and iron. And so each of those elements, they emit light at specific wavelengths, as you'll see, as I'll show later. And so here I'm pointing out a line of hydrogen, where it's really bright there. And this is both bright in the nucleus and other parts of, and so you can that's why it stands out so much. So the star is emitting it has a lot of hydrogen emission there. Okay. So now I'm going to talk about Python and how I use Python to analyze this data. So the first thing I did various things. I extracted spectra to get a rough idea of the elements that this object had. I also extracted slices of the image cube, an image slice at different wavelengths as well, and I'll show how I did that. And I also compared our observations with some observations by Hubble, and I'll show that at the end. So the first thing I'm going to talk about is spectral extraction. So here, and maybe it's a little small. Let me see if I can make this a little bit bigger here. There. Is that fine? Yeah. Okay, so here, first thing I did was import some necessary modules to perform the spectral extraction. Some of these that I want to point out specifically are ApLpy, which is a module that has a lot of tools astronomers use to analyze data. And LinePlot ID, this is a useful tool to label spectra on a plot. So the first thing I did was load data. So this is loading a FITS file. So I'm opening the FITS file, and this, in this case, called an HDU list object. This is the highest level of a FITS file. This consists of the data and an extensive header. So once I extract that, I can take the data. In this case, I'm picking a region of one of the slices of one of the image slices in the data from the NIFS. And I'm also getting the header. This is for the central regions of Hb12. And then I'm picking out the header information that I want. So I want to, computing a spectrum, and I want to calculate a wavelength range. So I'm picking the wavelength, minimum wavelength and maximum wavelength header values. And from that I can calculate an array, make a NumPy array for the wavelength range. I'm also extracting just one line just to sample the flux, how bright the object is at that point in the slice. I did that for field 1, for field 2, and also for field 3. I forget exactly, but they can be pretty large. Especially these, maybe like a megabyte or something. These can, because it's a Datacube, it consists of a lot of data. Like it's not just Some on smaller instruments, they won't be smaller, but this data is pretty big. So here I'm plotting the figure. I'm going to set up the figure size, and the custom axes. So what I'm going to do in this case is going to plot 3 different spectra on the same plot. So I can say using, I can add axes using this. This tells me where I want to plot the data. So the first value is, this is the x position, so y position, 0.4, third value is, that's the width, and the last one is the height. Here I'm selecting wavelengths of interest for me, and these are the positions where I want to plot, where I want to label lines, in this case the lines of hydrogen 1, lines of hydrogen. Now I can plot the data and add a title and a Y label and set Y limits. I can do the same thing with plot 2 and plot 3. And then here's the resulting spectra. So here this is the first plot, and I'll zoom out so you can see the whole, all 3 of them. And so now I can just stack them up if I want to just compare. These spectra, I want to emphasize, they're not scientifically of quality here. It was mostly just used as a tool for us to be able to get an idea of what elements this object had, and what looks interesting to us. Something I want to point out, you can see the really strong emission lines in field 1. Field 1 is the central part of HB12. So, and the core. In field 2 here, the emission lines aren't quite as bright, and same thing with field 3. I haven't tried that. I'm sure you can. The plotting library I'm using here there's other plotting libraries as well you can use too. I'm going to discuss another one later that you might be able to use also, but yeah, I'm sure you can. So now I'm going to talk about extracting an image slice from the Datacube. So in this case, I'm going to pick an element of interest that this object is emitting, and from that specific wavelength, pull out an image of that wavelength. Sometimes astronomers talk about that as like a narrow band image. You're just interested in just one region, one wavelength. So now I'm going to import the necessary libraries. Some of these are similar to the previous step. I'm using I'm import the first one, the APLpy. This is a useful plotting library for plotting FITS files and making them publication quality. So now I'm going to load and shift the Datacubes. The reason why I do this is because if you saw that funny pattern where there's of our observations, we have the nucleus, observation on the nucleus, north of the nucleus, and below. Well, I want to combine all these Datacubes. I want to make one big Datacube to make it easier to just pull out information from just one slice. But this meant that I needed to do some modifications. What I did here was I read in the Datacube and the header, but I'm also adding padding the data as well. This is to account for the shift, for a shift in the east-west direction. So I'm creating a pad using a NumPy zeros array, where the size is defined in terms of the header values. And the first value, that's the z-axis. So it's wavelength. And it's kind of what's a little confusing here is the header values are kind of backwards from the NumPy values. So what NumPy thinks is X, the header thinks is Z. So that's why it's a little funny here. But anyway, so I'm specifying here my NumPy array, and then I'm going to use dstack to put those two, that data cube, that pad, next to the data cube 1 for the central field. I also had to slice off some of the bottom of this data as well. So if you remember, some of the observations overlapped. So that's why I did this, sliced off the bottom of the data cube. Now I do a similar thing with the second position. I read in the data in the header. I also create another pad, and I pad that data onto the data cube and create my next data cube. And then I do a similar thing for data cube 3, except this was a little more complicated because I had to pad both the left side and right side of the data cube as well as the top. If you remember, position 3 was kind of in the middle and offset a little bit farther down. So now by doing this and these complicated steps here, I was able to align the data cubes so that spatially all the data cubes and the data matched with the sky coordinates. So I can now be sure that I can accurately pull out an image at a specific wavelength that matched the image coordinates on the sky. Okay, so now I'm going to stack the FITS files. So now I'm going to stack each of the data cubes. And I'm going to modify the header because now since this data cube large data cube is bigger, I need to modify the header values to reflect that, the new size. One second. So now what I need to do is compute the wavelength range. Because I need to define a wavelength range in order to be able to figure out what wavelength I want to extract. And this is a similar step to what I did with the spectra. And now I'm going to define my parameters of interest. I want to subtract a decided line of iron 2. Produces a very pretty image of Hb12, and I'll show that in a minute. This is the wavelength. This is the wavelength in microns. But I'm going to convert this wavelength scale to velocities. Oftentimes, in this case, since it's an object that's expanding, and we're more interested in looking at this object in terms of the differences in velocities. Where I can say for that specific line of iron, that's a velocity 0. And if emission is coming towards us, then that means that the velocity is going to be negative, and it's going to be blue shifted. And if the velocity, if it's going away from us, then it's going to be red shifted. So now I'm just changing the wavelength range, the scale, in terms of velocities. And I'm saying, well, how far off of the line do I want in terms of velocity? Here I'm saying that I don't want to get a slice from the 0 velocity, but I want to slice at 30 kilometers per second away from the line. So that's where I'm saying finding v shift. And then and the bottom I calculate the exact pixel. So now I can be pretty certain that I'm pulling out exactly where I want to pull out this image in H2 of Hb12. And now I can pull that slice out. So here I'm just taking, at pixel position, I'm taking out a two-dimensional array, and I'm storing that in Datacube cut. Now this image doesn't just include, it doesn't do just emission from iron. It also includes emission from the star as well. If I'm interested in only seeing the iron emission in Hb12, I need to subtract that emission from the star out. So how can I do that? To do that, I'm going to select from that wavelength of iron. I'm going to step a little ways away in wavelength, where I know at that wavelength I'm sampling emission just from the star. So in that case, that's what the wave continuum here is in wavelengths. And then I calculate here, I calculate the pixel positions for where I want to sample the continuum. So now I am pulling out two other slices, image slices, but in this case, this only contains continuum emission. Is on either side of the iron line. I'm going to put these together and then median combine them to produce a median combined image of the continuum. Now that I have this, I can subtract that from the image and get a continuum subtracted image of iron 2 at plus 30 kilometers per second of Hb12. Here I modify the header. Important things I wanted to point out here is in this case I just copy the header from the large data cube, but the FITS file that I want to save is two-dimensional, so I'm just deleting the header values that have to deal with the third dimension. And also I'm saying that's a two-dimensional array. So that's what this value is here. I'm going to write that to a file. And now I can display the data cube. I can display the slice in the data cube. So here I show what it looks like. So this is an iron 2 image of Hb12. What I want to point out is you can still see it's still right in the center. It's so bright it's hard to subtract all the light out from the star. But even that, there's some iron 2 emission there. You'll notice the lobes. You can prominently see the lobes here of the hourglass shape of Hb12. So go into little details of how I made this plot. Here I'm using the APLpy package, and from that I can load in a FITS file and set the figure size. I can add a label, say what color I want of the label, and I'm adding two labels here. And then I also put the setting that I want the x-axis, I want the y-axis, to be in arc seconds. So this is pulling out information from the header. With this package, it's using information from the header to be able, because the header contains information in terms of that translate the pixel size to sky size, how big that corresponds to how much of the sky you're seeing. And here I'm saying the color map I'm using is a heat map. I chose that because it really emphasizes the nebula and the emission. And so that's what it looks like. So finally, I'm going to talk a little bit about some more the plotting routines that you can use. Yes? Oh, right. You can, what I'm showing you here, I'm doing it. It was, yeah, this here, this is what I'm showing you here is hard-coded. The program that I wrote is interactive. I didn't want to go into all that detail there to show the interactive, but the way I had written it to make it easier was to be allowing the user to enter in what emission line they wanted, how far off of that emission line they wanted to extract, and then produce it. Here I'm mostly just showing you how the code works. So yes. The file format and FITS format. It's what's pretty standard in astronomy. I don't know. I think it depends on. They can hold a lot of data. I can't remember off the top of my head how much. So, but yeah, megabytes, not terabyte size. So that each data file is in a few megabytes, but yeah, not terabyte size. So, and also it depends on the instrument. If it's a really big instrument, then it'll be bigger if it's filed. So, there's one file. Yes, exactly. So, yes. To record it, or well, so I guess the way they answer that, depends on the observation. So when the data, these data, the observations were taken anywhere between 20 seconds and 100 seconds. So and that's how long, and so after that, then the data is saved. But in that case, each pixel is just recording the light that hit the detector, and so that's what. So these pixels, this is an array of 4,000 by 4,000 pixels. So, right. So. Okay, so now I'm going to apply a square root grayscale plot. And I'm also going to overlay a contour. So here I can set the figure size. And I'm putting, in this case, different aspects about the plots, as mentioned before. And here, this is what the image of the nebula looks like from Hubble observations. I can also apply a log grayscale stretch. So here I'm saying the stretch I want to use instead of square root is log. And finally, I overlay a region file. And in this image here, so what a region file is a file that you can, if you just want to draw on the FITS image, it's one way to do it. And here I'm showing you in this region file the different pointings, NIFS pointings overlaid on a Hubble image. So here I can load in the region file. and then I can display it here. Okay, so now if there are questions about the coding, I'll go back to the other talk. Okay, so now I'm going to finish by just discussing what we learned scientifically from this data. So here what I'm showing are, in this panel on the right, at the top, all these are image slices. At the top is emission in iron. The second one down, this is H2 emission. The third one down, this is helium emission, and the bottom is hydrogen. And you'll notice that the iron 2, and from left to right is going from minus 90 to plus 90 kilometers per second in steps of 30 kilometers per second. And so you'll notice, some things to notice here is the lobes are most prominent in iron 2. In the helium 2, you can see arcs of emission. And that's it. Very little emission there. And that's H2, it's molecular hydrogen. And the helium, the hydrogen on the bottom, those are just dominated by the really bright nucleus. This is zooming in on the core. On the top, this is helium emission, and the bottom is hydrogen emission. And you'll notice in the upper left, in some of the frames you can see what look like two lines, vertical lines. We interpret this as being an inner torus. So you can imagine like a donut in the center. And the mission there is the outflow is going through the torus and then going out. It's like a fire hose, basically, like the nozzle. And this torus, it's 30 times narrower than the width of the hourglass. So the outflow is just zooms out right away. Here I compare the HST images with the NIFS data. This is a molecular hydrogen image of HB12 on the left from HST, Hubble telescope. And on the right is NIFS. And you'll notice those arcs of emission there that you can see both in the Hubble image and in our NIFS image. So to conclude, I gave an introduction to planetary nebulae and how integral field units work. I demonstrated how Python can be used to analyze Datacubes, the Datacubes data that we acquired with NIFS. And at the bottom, and I also talked about the scientific results, what we learned from our analysis. We learned that the lobes are bright in iron 2, that the north lobe is red shifted and the south lobe is blue shifted. So the nebula is tilted like this. And the core is dominated by bracket gamma, the hydrogen emission, and helium emission. And also, as I showed with the plots of the core, that it has a very tight, narrow core, inner core, that's 30 times narrower than the lobes. Any questions? It's becoming more popular. It's because I think it's because Python's becoming more powerful. There are other languages out there that can be used. One of them is called IDL, and I actually used that during my doctorate at Florida. And it's very good for working with arrays. But the one thing is that it's the license is kind of expensive, and you can do Python's free, and Python's becoming more powerful, so you can do a lot of similar things. So Python made sense. That.
Are day you mentioned that the image is 4K by 4K, and the pixel depth is 16 bits. Does the pixel depth and the dimension affect the analysis? For example, smaller 2K by 2Ks versus 16 by 16Ks, and the pixel depth 8 bits versus 16 bits. Does that affect your analysis?
I mean, it might make it a little bit. It might make it a little bit slower, but in this case, in astronomy, when speed isn't necessarily as important as in other fields, that's okay. It's not going to affect the science as much, and mostly a lot of that depends on the instrument. It's whatever if it's an instrument that's bigger and it's going to produce more detailed, finer pixels, then you're going to get maybe more detailed information about the object. If it's a smaller telescope, smaller instrument, the pixels will be bigger, and the data won't be quite as comparable. So a lot of it depends on the telescope, the instrument that you use, and that will govern what data you get. So.
I'm curious, what's the state of the Python code that developed as part of this? Is that available, or part of that available for others as well?
Well, I haven't. All this code I wrote on my own, I haven't made it available yet, but I'm considering I put it up on GitHub and people can use it, look at it. That would be fine with me. Yeah. This one or?
What you did is you take a picture, you slice them up, you dice them up, and
Yes.
you produce another picture, which is part of the original picture. Is there an additional way of analyzing the data without having to look at the picture at the end?
I mean, some of it depends on.
Additional signal processing, like use Fourier transform, for example.
You might be able to do that. It kind of depends on what science that you're interested in. If you're interested in looking at maybe in periods or something, you might want to do a Fourier transform. In this case, where we're interested in the structure of the nebula and we're interested in what it looks like at different wavelengths, that's where we chose to pull out slices. So a lot of it depends on what kind of science that you want to do. Yes, exactly. For this, you do. Because for us, for our scientific goals, that was to analyze what does this nebula look like? How does it look like at different wavelengths? So that's why we chose to analyze the Datacubes that way.
If you have questions, it's a good idea to come here in the middle. We have a mic set up so everyone can hear you. Sorry for not telling you that earlier.
I have a question about astronomy. So someday our own sun will become a red giant.
Yeah.
And then a nebula. Mm-hmm. That nebula that is in our future, how does that compare to this one? Will it be larger or smaller, or do you know?
I think it'd probably be smaller. It's hard to tell. But the thing in this case, this star is, I forget the exact, but it's bigger than the sun. So when it was a star before it formed Planetary Nebula, it was bigger. In terms of the Planetary Nebula the sun will form, I don't know. I mean, the thing is, the astronomers are still trying to understand why they have such interesting shapes. Why planetary nebulae, they have hourglass, very distinctive like this. Lots of bipolar outflows. They have rings. Some of them are just spheres. And we still don't know exactly why they look the way they look.
Another quick question. So the Earth is made up of a lot of elements that are kind of heavy. Like certainly iron is one of them.
Yes.
Is it, in your opinion, would an Earth-like thing come about from this particular nebula, or would it be something different? Because this seems like, okay, you've got hydrogen and then you've got some iron and some, but I don't see any silver in there or gold or anything like that. So do you think the Earth came from something different? Or would you just say, I don't know?
Yeah, it came from something different. So when The Earth formed when the sun formed from a different nebula. So stars form from a big cloud of gas and dust. They don't form from a planetary nebula like this. And in that case, the cloud collapses and it forms the star at the center, an accretion disk around that star, and that accretion disk eventually forms planets. And then when it dies, in this case, like when it forms a planetary nebula, it just puffs off the atmosphere and produces a planetary nebula, and that's a lot smaller than the nebula that stars form from.
Hey, so in your example, you were showing that when you were trying to subtract the light, the core was so bright that it made it difficult to subtract all the light to just show the iron. But your final images didn't really seem to have that problem. So can you sort of talk us through how you controlled for the bright core?
Right. Well, in some of them, it still shows a little bit. It's just, let me see if I can go back. Oh yeah, I see what you're saying. I think in this case, it may have the one that I showed earlier. It could also be the display as well. I think it's because I can see here there's a little bright in the center. I think it must have to do with the display that you see in this image here. It's different from the other one, and it really, as you can see too, it's only in the 30-kilometer one off, the positive one off from 0. That's the only place where you see any kind of emission from the core. The rest of it you can see is pretty much nothing. So
okay.
Yes.
So the process that you use to generate these images is exactly the same as the
That's the
example.
same. Yeah, exactly.
Okay. Wow. Cool. Thanks.
Okay. Yes.
I had another astronomy question for
Okay.
you. Do you think or can you tell if the core in the center is rotating, and can you tell how fast it's rotating?
With our observations, you couldn't. So they do know there are other observations that do show that it has a binary core. It doesn't go around like in hours, so it takes.
So there's actually
But if
two bodies going around each other?
Right, 2 binary stars going around each other.
Huh.
So, right.
If you wanted to find like tools for FITS files or that kind of just play with this kind of thing, what do you recommend?
I would recommend using the AstroPy library. That's the main power horse that has tools that you can use for analyzing FITS files.
Right. Are there a lot of like FITS files just available online for these kind of things, or?
There are places. I think on Hubble site you can download data there. I'm trying to think of other places as well. Astronomers have, when you observe, you have certain priority time. So they give the astronomers like a year and a half to publish their results. And after that data is public, and anyone can use it.
Okay, thank you.
So, yes.
A little bit on a different tack. Did you do a lot of image processing in your work?
Well, I mean, this kind of image processing, yes.
And if
So
so,
that's
did you use Python, and can you suggest a tool to do image processing in Python, or what is your preferred one?
I mean, the most image processing I would say I did was working with these Datacubes. And so that was using, in that case, that was using just kind of like the steps that I showed, where how to pull out the images. You can also how to plot them, how to make plots, and change with the color scale and play with that. The astronomers themselves, when we get data, the data and the raw data, it's very noisy. It consists of data because when you're getting photons, but you're getting photons not just from the object of your interest, but photons that come from heat, especially if you're observing the infrared. You're getting photons from cosmic rays. And so there's a whole, I didn't show it here, but there's a whole complicated step where you go through a pipeline where you're taking the raw data and you're cleaning it up and you're transferring it and making it into something that's going to be scientifically useful.
Another astronomy question. You're saying that you believe that there is some kind of binary object at the core of the nebula.
Yes.
So am I correct in believing that the torus that is formed is in the orbital plane of those two orbiting objects?
Yes.
And so therefore the lobes of the nebula are also in that same plane. So if we were talking about something analogous for our own solar system, essentially, well, to either side would be kind of the top and bottom of our solar system, if you will.
Right, in terms of like the plane of the planetary
orbiting
nebula.
this way with respect to the pictures we saw.
They were orbiting this way. So let me see if I can go back.
That's interesting.
So, oops. See if I can get back. So here, where I'm showing north-south is up-down. The torus is aligned east-west. So what you're seeing, the reason why you see what looks like where these two, what you're seeing are the two walls of the torus, the two vertical lines, and the hole is going this way. So it's just because you're looking through. It's brighter there because you're looking through more of the torus. It's thicker, so there's more emission. When you look through the center of the torus, there's less emission you're looking through, and so it's not as bright there.
Okay, that makes sense to me because it seems like in a lot of astronomical objects you have things coming out of the axis of rotation.
Right, yeah, exactly.
Okay.
So that's what's going on.
Thank you.
Thank you. Okay, very much. Yeah.
So just wrapping everything up tonight, I really appreciate our speaker. Thank you very, very much one more time. That was awesome. What talks, I need a volunteer, someone who can keep notes. Someone really quickly want to take notes for me? It's really easy. Just write something down. Okay, good. Someone, here we go. Both of you. We'll compare afterwards. All right, so real quickly, I want to brainstorm with the group. What talks are you interested in? Someone tell me what you would like to hear here at BayPiggies. I know we have something already planned until June, but you know we still have people cancel and we also have room for later. What would you like to hear? Not what would you like to give, but what would you like to hear? Yes? Build automation, like BuildBot or any build automation. I have, yeah. So we talked about Ansible before, but that was a couple of years ago. Would anybody be interested in hearing about Ansible again? Oh, wow. I already have 2 slots on the calendar, though. Do people want to, maybe we'll vote something off. Yeah, maybe you don't want to hear me talk the entire time. So, but maybe Ansible, we can choose that one. Yeah, another talk. Deep learning, I love it. So we're writing these notes down, yes, so we can remember them later. Awesome. Deep learning. Anything else people are interested in hearing? Stephen.
We're discussing talks, and I just want to have a couple announcements afterwards, so I will wait until we're done with this topic.
Great, great. Well, let's quickly get a brainstorm for other talks. What about web frameworks? We've heard of web frameworks out the wazoo a few years ago. Everyone was always talking about a new web framework on Python. Is that old news now, or is it like, oh yeah, tell me more about web frameworks? Yeah, good. I see lots of vote ups, like Django, bottle, flask. Oh, I hear a lot of emphasis on flask. Falcon, pyramid. Oh, I haven't heard pyramid in a while. That's awesome. Pyramid. Anything else we want to hear on these frameworks? Yes, yes. Bouquet. Anything else we want to hear? Yeah. Data analysis. Definitely like that. So here's a trivia question while we're waiting for more people to percolate all these wonderful ideas to talk about. What, besides the normal slide presentation, what was the actual tool being used to show data on the screen?
The notebook.
IPython Notebook. Awesome. Yay. So maybe someone can talk about IPython Notebook, or is that old hat now? Oh, I'm sorry. Wow. +1. Yay. Oh, +2, 3, 4. Okay, that sounds really good. So that's awesome. Boy, where have I been? Yeah. Functional Python. Very cool. Very, very good. Okay, we have, yeah. So Python versus R and comparing them? How do you go from R and how does it compare to Python? I'm hearing a lot of data science the last few years. Is that a shift that we've been seeing a lot more of data science? But yeah, R to Python. Cool. Stephen. Pandas? Yeah, I've seen some talks recently on pandas. Is it old hat now or is it all exciting again? Do we want to see pandas? Yeah? So people would still come to those talks. All right. Any others before I quit with this one? Natural NLP, natural language processing. I know someone who literally wrote the Python book on that. Maybe I will see if I can twist an arm or two. So NLP would be interesting, yes? Oh, functional and unit testing. Cool. What about a testing on how to do red, black, green refactoring on actually test-driven development in Python or behavioral-driven development in Python? Yes, no, maybe? Ish. Yeah? A lot of emphasis over from the LinkedIn group. Awesome. All right. So, well, I'm thinking, for example, Behave, the Behave tool. So instead of Cucumber, but in Python world, using Behave, maybe? Oh, yeah. Okay. Yeah, go ahead.
And my suggestion is MicroPython on specific hardware.
Oh, Raspberry Pi kind of stuff? Or yeah. Okay. Cool. What about lightning talks or smaller talks? Any +1s or -1s on that one?
So actually,
a lot of +1s on that one.
So we used to do something called Newbie Night, and it was specifically like bring a friend and it's safe and, you know, we won't beat up on you and stuff. And this was pretty cool, and it just sort of fell off the agenda a few years ago.
All right.
We used to kind of try to run it every like 4 or 6 months.
How about some beginning talks?
And sorry, Glenn, especially also as a motivator to encourage people who are long-time lurkers and haven't spoken and stuff. And it was a great way of connecting new people.
Yeah, I think it's a great idea. Also,
Do we want to have show of hands on Newbie Night?
Oh, it's Newbie Night hands. Definitely like that. Newbie Nights. How many people are just learning Python for the first time or who'd say they have less than a year's experience in Python? A good chunk of the crowd. Okay. Less than 2 years of Python. Less than 3 years. Okay, less than 5. Okay. So Newbie Nights for sure, and a lot of beginning topics might be really good as well.
Yeah, so suggestion on that. So Project Euler, dive into Project Euler is a graduated series of programming experiences. Okay. And then there was, what was the Python, the one where they generate the URLs?
Oh, the
Python Challenge. What was it called?
The Python Challenge.
Python Challenge, Project Euler, SPOH is Spear Programming Online Judge, and it's kind of interview grade questions in Python. So, you know,
great stuff.
So not that you do all 138, but pick a few selected ones and crank them.
Sounds great. Zincones in Python? Okay, cool. So lots and lots of good topics. In fact, if you're more interested in the beginning track, our next talk next February, in February, not next February, we're going to be talking about our speaker's right here, and it's going to be a quick synopsis. It's going to be more for beginners. How do you do stock market stuff with Python? Yeah, so if you're more of a beginner crowd, that's what we're going to have too. Right, so real quickly, I got a lot of stuff, and I really appreciate the people who are writing it down. Anyone, I remember when I first did, I guess it was a South talk. South is a part of Django that you actually can do data migrations. I wanted to know how to do South. I had no idea how to do South. It's something I kind of wanted to learn, and I wanted to give a talk on, mostly because I wanted to be forced to learn. Because you can be like, yeah, I want to learn South. But then suddenly, you know, you have a talk coming up in a week or a month. So any of those people who raise their hands and say, we'd like to talk about this, would like to give a talk to say, hey, yeah, I can talk about that. Any volunteers? Sarah? Was that a volunteer? Oh, no. Nope, sorry. Yeah, Vicky. All right, newbie nugget on zip functions. Anybody? Yeah? Anything else? All right, I have a couple of talks. I heard 3 things mentioned tonight. I want to cut one off just so I don't be the one talking so much. One of the talks is going to be about how to use Git. You take, like, Git itself. I will show you. In fact, I have a contest I'd like to announce, which I'll talk about that one last, so I'll pause on that one. The other 2 talks, one of them is Ansible, which we could talk about. I could do one here. And the third one was, someone help me. What's the third one slated? Oh, a Python and Ruby group to get together. If you know Ruby, you want to learn Python, learn Ruby. How many people, of those 2, and then the Git I'll talk about, which one of those that you don't want to see? So I don't talk 3 times. You won't hurt my feelings, I promise. Ruby's going out the window? Okay. Fair enough. So, I have a quick announcement, then you can do a quick announcement, then we'll be done. Sorry for talking so long. So the announcement I have is I have a contest. I have a talk I'm going to give. I will teach you and have videos already to show you how to do this by the command line. So how do you go into the Git subdirectory, which is actually a repository, and see the head variable? I'll show you. How do you take that head variable and actually go to your branches in the refs subdirectory? I will show you. How do you look at that head and refs and actually go find the commits in the commit object and be able to see what that is and actually look at the commit object? I will show you. So I will give you everything from the command line you can do, and you actually, as the contest, need to do a git log in Python. I have an open contest. I have no idea what the prize is, and I will send an email out. So if you're interested, I will show you how you can do git log, throw the git command away, just for a little bit, for fun, and how to do git log in Python. With one caveat, there is one plumbing kind of tool called git cat file that we have to use. But besides git file, you'll never use the git command. You'll do it all with Python, and it's a great learning tool. So if you're interested, there's a contest. I don't know what the prize is going to be. I've got to find something fun, but it would be great to find submissions for that. You have an announcement?
Actually, I have 2 announcements. The She's Geeky Unconference for Women is going on tomorrow and Saturday at the Computer History Museum. It's technical and non-technical. It's an unconference, and so we don't know what people are talking about. But I've talked about Django, and I've talked about bees and whatever, and I'm sure you can, if you're a woman, sign up tonight or walk in tomorrow, shesgeeky.org. The second thing is I just met, Glenn just introduced me to Sarah, and I'm also interested, Sarah and I are mutually interested in getting PyLadies in the South Bay back going again. There was something at LinkedIn for many months that was interesting, and then Rachel left, and that kind of died. So if you're interested in PyLadies, meet under the Big Blue Inn right after I stop talking.
Awesome. All right, thanks. Oh, there's another announcement. Tony.
It's not an announcement, but if anybody here has worked with the Python C API, I have a little problem. I need your help. Thanks.
Any last minute announcements? All right, thank you, everyone. It's awesome.